Hi, this is Lab 2 for Projectile Motion. For this lab, we had to throw some object, projectile, and we would calculate the different forces that are acting on that projectile. We threw a paper ball, and this was the easiest thing that we could find, and we threw it right above a meter stick for calibration for the tracker app. And here's us throwing the said ball. Keep in mind for the camera shaking for a little later. Initially, the data did look really good. The position in the x direction looked like a straight line, and the position y direction looked like a quadratic, which makes sense because acceleration is meters per second squared. When plotting down the actual graph, it's going to be this orange line. It goes about the same. It should go exactly the same as this line right here. It is just a copy and paste of that. This computed line, however, is what we got when we put the initial velocity in the y direction and had the force of gravity acting upon it. As you can see, it does look like it's going to end up short of the area where it actually did. This will start to cause a problem when we get to drag. So in doing drag, the way I approached it was I was going to use the x direction and see how much the difference was between the computed model and the actual model, because there's no other force other than drag in the x direction. I wouldn't use the y direction because you have gravity, and that would be a little bit more complicated. And you could, if you find drag in the x direction, the coefficient x direction is going to be the same in any direction. The coefficient, it's the velocities, don't think that's going to change. I calculated r's to be negative because the position at when the actual landing position is 0.786 for the actual landing, the computed position is only 0.7. This means the actual distance was further with air resistance than the model that did not have air resistance. This means that in context, it kind of means that air resistance was pushing the ball forward, although I believe it's because of camera shaking that the calibration was set off, and that at the end of the day this number is going to be meaningless, because what happens in the x direction, if the camera is shaking, it will probably not happen in the y direction as well, and there's no way to really calculate that. The way I calculated them, however, was I found the difference, which is 9 centimeters. I used a kinematic equation to find the acceleration. That turned out to be 0.56 meters per second squared. Then I plugged it into force times mass. The mass of our ball was 3 grams, and so our F drag in the x direction was 0.00196 newtons. We finally placed it into the drag, force of drag equals to negative b velocity squared. Using initial velocity, I thought that was the best one to use. I got b to be negative 0.0018. If I got an actual drag value, I could have calculated the terminal velocity by using the drag force formula and just setting it equal to the force of gravity and having the velocity be our variable. That way, whenever the two were equal, at whatever v they were equal, that would be the velocity that would be the terminal velocity. If the ball was thrown straight up, it would take longer to hit the ground again because of the kinematic equation, where instead of our final, we have the height equals velocity times time minus 1/2 acceleration due to gravity, t squared. Since v is only the vertical direction, we do not have to worry about the x direction in this case. If you take all the same speed in a direction that's both in the x and y direction, but then you switch it to just one or the other, then that direction is going to have more velocity. And as you can see, more velocity would relate to more height, which would mean more time to then have to take down the ball again.